About the problems, apparently I forgot to download or upload all the questions that I looked up from the textbook. I'll get those posted later today because I definitely have a list of all of the questions from the textbook. I just forgot to transfer them across. What we're really looking at is kind of the overlap between chemistry and physics, okay, at this point. And when we go all the way back to the 1800s, they kind of had an idea of light, primarily from pictures. Okay, so they were able to develop or create different plates with silver nitrate. When you expose silver nitrate to different wavelengths of light, it changes its appearance, and you get a black precipitate, and that allowed for ultimately pictures. Okay? So it was kind of the study of that that kind of made things interesting. Okay? And so they kind of wanted to know more about what was happening with pictures. What was light? We had a rough idea of electrons and protons. We had no idea where they were, so we didn't have an understanding of what a nucleus was or even what an atom was. We just knew what the pieces were. And as far as the pieces go, it was just protons and electrons. Okay? So someone came along and said, okay, let's see what we can do as far as making a stream of electrons. So they were able to manipulate those a little bit better, so they figured, let's see what we can do. Okay? And one of the big inventions they came up with was a cathode ray gun, if you will. Okay? This single piece of equipment is probably what started most of our understanding of the nucleus. Okay? So what happened with this is that we take a tube of glass, and what they found is when they pumped electric current into a particular sample, that it would off or release an electron stream. Okay? So that was kind of neat that they could get this. However, typically that electron stream was highly, highly unstable. Remember, electrons we can't dissolve. So in most circumstances, when they generated this electric current, what happened? The electrons would immediately hit an atom and die. Okay, so or not die, but we wouldn't get an electron stream anymore. So the thing that really allowed for this to occur was that they built a vacuum. Okay? So all science boils down to a vacuum. So why is that important? Well, to generate the electron stream, because it's so unstable, if there's an atom in that position where the electron is moving through, the electron reacts with that atom, and we don't get that stream of electrons. So why is a vacuum important? Well, what can a vacuum do? It can pull out all of the atoms out of that individual space. Well, if there's no more atoms, what can happen? Now the electron stream can freely pass through, or pass through that space. Okay? One of the things they ended up finding out is when they built this, they noticed that one end of it would start to glow when you put it into a dark environment. And what ended up happening was that electron stream went to the end of the glass and would excite the glass, and the glass would begin to fluoresce, okay, or glow in the dark. So it was kind of a neat phenomenon. They had a lot of fun playing around with it. It's what actually gives us our old school televisions, or even old computer monitors, are all cathode ray tube built. Okay, so we ended up putting together thousands of these to generate individual images. Okay, so it's kind of an old technology that was then developed further for our own boredom. Okay, so eventually someone got bored playing around with this and decided to test the theory. Okay, and what he was curious is, do we still get this electron stream if we can't see it? Okay, so for some reason he took one of these tubes, which is technically a Crookes tube, and wrapped it in cardboard paper. Okay? Well, in theory, that way you can't see it, so we don't know what's happening inside it. And so he fired it up just to see what was going on. Luckily enough, depending on who you talk to, I'm sure the experiment was a little bit more scientifically based than this. He had some silver nitrate, so film paper, lying around at the end of this tube. And what ended up happening? That paper started actually changing colors. Okay? So everything was blocked off from this tube, so electrons couldn't pass through it. And now all of a sudden, some paper that's supposed to respond to light is now changing colors. Well, there is no light. So what he ended up finding was actually X-rays. Okay? And it was this initial presentation of X-rays and the initial discovery of X-rays that then led to a bunch of other discoveries that pushed along after that. Okay? So they played around, understood electrons, had an idea of protons, And now they started to come up with a new form of energy. Instead of light, we now have X-rays. So people wanted to play around with X-rays. Where are they coming from? Why do they exist? Those kind of big, broad questions. Okay? So it was this kind of discovery that allegedly led to the curiosity of two people, Becquerel, and you've probably heard of Curie. Both these people were working on the same general principles of radioactivity. Okay? So it was this initial invisible energy that they saw with X-rays that piqued their interest, and they said, okay, there's got to be something else going on here. And they started to look for other sources of this invisible energy. Okay? It turns out that they ended up stumbling and studying across radioactive materials, because radioactive materials can generate another invisible form of energy. It turns out it's not an X-ray, so X-rays are not nuclear radiation. They just happen to be similar enough as far as the invisible energy goes that they tied those two interests together. Okay? So that's kind of the birth of where we're going with most of this material, or all the things that we're going to study with this, is looking at these radioactive samples. Okay? So Curie, in her own right, was actually quite an interesting person. Was interested in that light passing, or not light, that energy passing through samples that we couldn't see, and wanted to find it, come up with other sources. And so what she ended up studying were things like uranium, radium, polonium, pretty much all of our standard radioactive particles. She ended up studying more and more. Okay? Some of the interesting anecdotes when it came to radiation was that she famously died, probably from cancer, because she would carry around samples of uranium or radium in her shirt pocket. Okay? So things that are now extremely controlled that we can't even get near in our nuclear power plants, she was carrying around in a little shirt pocket saying, oh yeah, whatever, not a big deal. Okay? Because they just didn't have an understanding of how dangerous these compounds were. Okay? It's invisible, it can't hurt me. Okay? Not always the best statement. Okay? So in her process of going through and studying these radioactive particles, her information and her knowledge ended up expanding the fields of science so broadly that she actually won the Nobel Prize twice. Okay? There's only one other person that's won the Nobel Prize twice, and that's Linus Pauling, also fairly interesting, also a chemist, okay? Chemist/physicist. So these two fields you can generate a lot of information from. So in the process, she won it for physics and for chemistry. One of those awards came from the discovery of, I believe it's radium. I put that on there, which I think she's got, oh, there it is. The discovery of polonium and radium. Radium ends up being the more important one, okay? The reason being not so much that she was part of that discovery, but that she was able to isolate it in a pure form. So whenever we're going through with our lab experiments, one of the things that we like to do is to simplify. We have to control every single possible variable. So if we're going to try and study radioactivity, we need to make sure that the sample we're studying is pure. So that way, if something comes out of it, we know where it's coming from. It's not coming from some other random source. Okay? So when she went through and isolated radium, okay, why was that important? Because she was able to generate a very pure sample of radioactive material. That very pure sample could now be used to study other processes. So that information, the ability to isolate and purify the sample, is huge technologically speaking. If that discovery were made today, any ideas how much we'd know about the atom? Probably close to nothing. Any ideas why? Because she didn't patent that information. She left it freely available for everybody to go ahead and use, so that other people could now take advantage of how to isolate that pure sample and now try and discover other things. In particular, one of the big discoveries was Rutherford. You remember Rutherford's experiment from 151 or 113? What did he end up doing? I guess you remember really well. Okay, that's good, so when I screwed up, it doesn't matter. He ended up bombarding a gold sample, a thin gold film, with radioactive particles. Okay? And what was he hoping to see? Well, he was trying to discover how a nucleus, or the creation of an atom. Was it the plum pudding model where we had protons and electrons floating all over the place? Or did we have a dense nucleus in the middle? So he took that radioactive sample and fired it, or directed it towards the gold film. And if it was the plum pudding model, what would happen? Our radioactive particles should pass directly through. No real deviations, because there's nothing of any particular mass that would hold it or kick it anywhere. And we would see the back of the sample, or our detector, respond to the radioactive material. Okay, we could see our silver plates changing colors. So he set that up and did it, and what did he end up finding? He noticed that when he surrounded the gold foil with these plates, our silver nitrate plates, what ended up happening? He saw that parts of the plates actually started developing much, much further back, almost directly 180 degrees away from the plate, where they expected it to hit. What does that mean? That means those particles had to impact something of a significant size. Okay, well, if your atom is just electrons and protons floating around on their own, there isn't anything of really any large size. So what does that mean? We had to have a nucleus. We had to have something massive enough that when the radioactive particles came up, they could hit and bounce. Okay? To be able to discover that nucleus, to be able to do that experiment, they needed to have radioactive material, and they needed to have a pure sample of it. Without that pure sample, you cannot run that experiment, okay? Or you cannot make any conclusions from it, because we don't know what particles are coming out of that radioactive sample. Okay? So a lot of the advances that we now look at and take for granted, like the atomic structure, that came from an understanding of radioactivity and the manipulation thereof. Okay? So a lot of science, as we know it, comes back to Curie, okay, and what her understandings were. If we get rid of what we understand to be a nucleus, we probably also destroy the ability for Einstein to go through his theories of relativity. Okay? So it all really boils down, depending on who you talk to this one woman's success. Okay? What makes this, in my opinion, even more interesting? Okay, come on. Talked about all that. Oh, I didn't put it up here anymore. What I think this makes this even more interesting was that consider the time frame that this was occurring in. I think I've got the date up there, late 1800s. How did I not include this? Late 1800s, early 1900s. Okay. If we think back to even, I think that's just hit the news 40 years ago, 1970s, 1960s, women weren't allowed to be astronauts. Okay. NASA sent out a letter to applicants, female applicants, and said, nope, you can't be an astronaut because you're female. That was 40 years ago. 100 years ago, what's the odds that a woman could even get into a scientific lab? Okay? So she went against huge odds to be able to come through, discover these kind of things, and then actually have the wherewithal to not be like, screw you, I'm not going to give you any of my information, but then shared it as well. Okay? So the amount of just sheer amazingness of this woman is actually really, really impressive. Okay? So I would highly recommend that you read up on her, because I think it's actually an interesting story on what's going on with it. Okay? To give you another idea of what's going on, she was French, I believe. She won the Nobel Prize twice, so a world-acknowledged award. Okay? French Academy of Sciences said, no, you cannot be a fellow of our little club. Okay? So even within her own time, she was being excluded from a lot of these really important scientific discoveries just because she was female. Okay? So there's a lot of interesting backstory behind her. I would recommend you take a look at what she's discovered and what she's done. That's kind of just my little spiel on it and where a lot of this information ends up coming from. It comes back to her and Becquerel and her husband, I believe. Okay? She was one of the first ones that noticed that we could generate electric current with radioactivity, which led to the discovery of the Geiger meter. Okay, so how we actually monitor radiation. And you know those little clicky things. Those clicky things are based off of understanding that radioactivity generates electric current. Okay, and that's what they're detecting with those clicks. So yeah, important story. You should be aware of it. Okay? The biggest part of that, I think, is ultimately the discovery of the nucleus. And that's really what this chapter is all about, is the chemistry involved in that nucleus. Okay, so we've done a nice little history lesson on what's happening there. So we'll go all the way back to 151 and look at the structure of an atom. Okay? So a lot of the stuff that we've looked at, or that you've seen before, is electrons, protons, and neutrons. To build an individual atom, our electrons, typically, I would recommend you memorize as defining the charge of the element. Okay, so to move from one different oxidation state to another depends on how many electrons are around that individual atom. If we go through and look at the number of protons, the protons are also important to the charge, but if we change the protons, it doesn't change the charge of the atom, it actually changes the atom itself. Okay? So I would consider protons defining the element, not so much our charge. The very last species that's important when we look at an individual structure is the neutrons, okay, which define the isotope. Okay, why do we have neutrons? No ideas? I thought I had a picture here. What makes up a nucleus? Protons and neutrons. What charge is a proton? Positive. What happens when we bring two positive things near each other? They repel. If we take a look at, let's say, bromine, 35. What does that 35 mean? There are 35 protons and 35 electrons for bromine 35. If we have a nucleus, we're taking those 35 protons and we're smashing them into effectively the exact same point. How do we get 35 positive charges near each other when we can't even bring two near each other because they repel? That's the point of the neutrons. The neutrons add an extra little mass that's not charged that limits that positive charge repulsion. So we can now pack more protons into the nucleus. Okay? That neutron is there to hold it and allow for that interaction or that repulsion to be minimized to the point that we can get a nucleus. So typically people refer to the neutrons as acting like a glue, physically holding each of those individual pieces there. Okay? So before we look at nuclear transformations, what we want to go through and do is look at the major players and come up with an idea on our notations. Okay? So electrons, protons, and neutrons. First off, what do you know of their charge? It's the charge on an electron. Negative, protons. Positive, neutrons. Neutral. Okay? So we could come up with individual signs for each of these. So we now have an idea on what's happening with their charges. Okay? Next part is mass. Do any of these particles carry mass? Okay? We would assume so, because if we go through and look at what makes up everything, we take a look at even what makes up the iPad, what different pieces go into it. Well, it ultimately boils down to atoms. Okay, well, if we say the components of an atom have no mass, then we would say the atom has no mass, and then this iPad, in theory, should never mess up my shoulders from carrying around all on one side. Okay? Because it would have no mass. So very clearly, these particles do carry some mass. That mass ends up being very, very small. So typically, they show it in kilograms. We'll discuss why we use the kilogram unit. Okay? So we can get these ridiculously small numbers as far as masses go. Okay? If we looked back to the number of molecules in an individual reaction, we're probably looking at the order of 6.022 times 10 to the 20 molecules per an individual experiment. That's a ridiculously high number, right? So what did we do? Instead of looking at the number of molecules, we shifted our thought to moles, which was ultimately just another way of saying 6.022 times 10 to the 23rd molecules is 1 mole. So we can condense that number into a different system. We come up with a similar way to do that with mass. please say I put that on the next thing. We shift it to what's known as the atomic mass unit. Okay? So when we come to the atomic mass unit, it's a little bit easier to understand. That's what we end up reporting for our molecular weights. Okay? We use atomic mass units to put these things together. Protons and neutrons have an equal mass. Electrons are so small that their mass is really, really, really tiny. Okay? So in this case, we've got it written out in comparative units. Okay? Well, if it's that small, how much of a mass is that going to contribute to the overall atomic or the overall atom? Effectively nothing. So in most cases, we approximate the mass of an electron to be 0. Okay? It still carries mass, but as far as a good first approximation, it's not enough to worry about. Okay? We now need to come up with a symbol for each of these. We've already started to pull some symbols on these. What's a good symbol for electrons? What's that? Epsilon. Epsilon is actually already taken with extinction coefficient. We've used it already this semester. Just E. Okay. E for electron. How about protons? Any ideas? P sounds reasonable. Neutrons? N. Okay. So we've got a general idea for those individual symbols. Right? I didn't step this as nicely as I hoped. You'll notice that you'll see a bunch of numbers show up on the left, both as a superscript and subscript. What do those numbers represent? They're going to refer to the charge and the mass of that individual particle. So that way we can condense all of this information into a single notation that allows us to interpret relatively quickly. What's in the upper left-hand corner? The mass of the particle. Lower left-hand corner, the charge. You'll notice that this is a different notation than we've seen before with every other atomic structure. When we looked at molecules, when we look at an individual molecule, where do we write the charge? Top right corner. Why have we shifted? Why are we putting it in a different spot? What's that? Why do we need a different notation? When we used charge in the upper right-hand corner for molecules, we were looking at reactions between molecules. What are we looking at here? This is just looking at the nucleus. So what we want to do is come up with a notation that is different enough from our standard notation because it's a different type of reaction. We're now looking within a single nucleus, not looking at a larger molecule or molecules interacting with each other. Okay, so our notation becomes slightly different from what we've seen before for that reason. Okay, so go ahead and take a look at these three problems and let's see if we can come up with a notation for them. We can go through the first one, or I can go through the first one. For helium, if I want to come up with a notation to describe the helium nucleus, I don't care about the atom at this point, we're looking at the nucleus. What's a good first symbol to start with? How about He? Why He? Because it's a helium atom. Okay, and the symbol for helium is He. In the upper left-hand corner, what should I put? Go general first. It should be the... Oops, sorry, I looked at the wrong one. It should be the mass. Okay? So what things make up the mass of a helium nucleus? Protons and neutrons. Where could we find that information? Periodic table. Where is it found on the periodic table? The number underneath on these two cases. So we've got a mass for helium of 4. Okay, we'll come back to the numbers in a second. What is the charge in the lower left-hand corner? What is the charge on a helium atom? It's kind of a tricky question. 0. What is the charge on a helium nucleus? 2. Which number should we put there? Why 2? Because we are looking at nuclear transitions. We do not care about the electrons on the outside. We are only looking at the nucleus. Yes?
How do you know that it's 2 or the...
We go back to the atomic number, I believe is what it's called. In this case, the upper right-hand corner. That number represents the number of protons and electrons in each atom. So helium has 2 protons and 2 electrons. Okay? We now have our notation for the nucleus of a helium atom. Okay, so let's try and do the next one. What symbol should we start with here? Why not Ni? Because, I mean, the second letter of nitrogen is I. Just checking. That's nickel. Okay. Upper left-hand corner, we put the mass. We could go to our periodic table and look at the mass. What mass do we see? 14. So we would take a guess. Say that's 14. What's the charge?
7.
How do we know it's 7?
7 protons.
There are 7 protons in our nucleus. Okay, that's how we made the nitrogen atom. Okay, how about chlorine? Cl. Next part. Let's do charge first. Charge is a little bit easier. And the mass? What is the mass of a chlorine atom? It says 35.45. Huh. Does that mean the mass is 35.45? No. Remember, to determine our mass, it's the number of protons and neutrons added to each other. Why do we have a non-whole number there? In each of the other cases, we could say the extra number was probably the mass of your electrons. Why do we have something that's completely not whole at all for chlorine? What's that? What we have to realize when we look at nuclei is we can put in varying amounts of neutrons and protons. Protons define the atom. Okay, so we can't change the number of protons. The neutrons carry no charge. Okay, the only thing they contribute is mass. So if we put in an extra neutron, that doesn't change the atom's characteristic, but what does it change? The mass. So as we get further through the periodic table, we can start to put in varying amounts of neutrons to try and stabilize that positive repulsion. So what ends up happening? If I can put in a different amount of neutrons, I end up generating a different mass atom. When we look at the periodic table, does it tell us the mass of a single atom, or does it tell us the average mass for all possible combinations? The average for all possible combinations. Okay? So when we go through and evaluate each of these things, we have to be a little bit more careful with that mass number. When we're lower on the lower numbers, so we're looking up at the hydrogen-helium level, the neutron-proton count balances out fairly quickly or evenly out of these, and we don't have to stress too much about it. It's that exact number. As we get lower in the periodic table, so higher numbers, that nuclear mass ends up getting larger and larger. We end up having to add more and more neutrons to kind of balance out and put those positive charges away from each other, which means there's a variety of ways that we can put in those neutrons and a variety of numbers or of neutrons that we can put in, which means we end up getting slightly different atomic weights. Okay? So how would we know for sure what the atomic weight was? Okay, at least as far as you're concerned, I'd probably tell you. I think for chlorine it's 34. No, I think it's 35. I'm not positive actually on this one. I know bromine. Yeah.
Doesn't the periodic table take a weighted average of what isotopes are most
That's
common?
what we just said.
Okay.
Yeah. So what we're going to do is average those amounts. We don't raw average it because we could have differing amounts for each. It has to be weighted according to how many of that or how common that atom type is. Okay? In theory, you guys remember that from 151? Based on the questions, that kind of sounds vaguely familiar, right? Okay. So we could go through and look at the individual structures or the names for each of those, or symbols for each of those nuclei. Okay. So if we go through and take a look at this, what is atom X? Ra, whoops, also known as, let's see, did I put it up there? Radium. Why would we pick that one? I know you were all sleeping through that first part of it, but why pick radium? Why would I put radium on this? It's radioactive, and it was likely the most important radioactive discovery. The purification of radium led to pretty much all studies on radioactivity. Might be kind of an important thing to remember. Who discovered that? Curie, just checking. Okay. So when we go through and look at these problems, you'll end up seeing the symbol for the element. You'll have your mass number in the upper left and your charge in the lower right. Lower left. Okay. So that sets up our notation as far as these go. So then why do neutrons exist, or even radiation? Well, let's stick with the neutrons first. Why do we have neutrons in our nucleus? Because the proton positive charges repel each other. Okay? To prevent that repulsion, or to minimize it, we have to add neutrons so that we can kind of separate those positive charges away from each other and minimize that repulsion. Why do we want to minimize that repulsion at all? What would our periodic table look like if we can't minimize that repulsion? Not nothing. Hydrogen. That would be it. That would be the only atom that we could possibly ever have. Why? Because as soon as we try to bring another positive charge into our nucleus, what happens? They repel, and we end up getting back to hydrogen atoms. Okay? So our neutrons are what allow for us to actually build larger and larger atoms. Okay? We need that extra glue. Okay? And if you take organic chemistry, you'll end up seeing applications of this kind of idea. Positives repelling positives, and positives being attracted to negatives. We can take that back to magnets. If we take the north end of a magnet and we put it up against the north end of a magnet, what happens? It repels. If we take opposite ends of the magnet, north and south, they attract. So when we're looking at atomic structure and reactivity, when we're trying to react individual molecules with each other, we're always trying to find a positive and a negative. And in the course of the reaction, what happens? We bring that positive and negative near enough to each other that we form a bond. Okay? So if we align the same poles, we get that repulsive force. Our neutron is there to kind of stabilize that. Okay? You can see that back in the Pauli exclusion principle when we look at electrons. We put electrons around an individual atom. Why is it important there? How many electrons can you put in an individual orbital? 2. Why only 2? Why more than 2? Or why more than 1? Because remember, electrons repel each other. What's the quantum number, the last quantum number? The spin state. Electrons spin opposite directions. That opposite spin allows for us to pair electrons within an individual orbital. Okay? If we didn't have those spin states, how many electrons would we be able to put in an orbital? Only 1, because we can't get the electrons into the same orbital because they would repel each other. So we need that opposite spin state to be able to pair the electrons. Much for the same reason that we have that opposite spin state, we also end up generating neutrons. Okay? So why does radiation exist? Okay, so we know why neutrons are there, but what happens as we get bigger and bigger? What's the most famous radioactive element you're aware of? Uranium. Where's uranium on the periodic table? 92, way down at the bottom. What does that mean about its nuclear size? It is massive. There are tons of protons and neutrons in that nucleus. Okay? Why would that nucleus be radioactive? What happens when we get two protons near each other? They repel. Okay? As we add more and more protons in, we can add more and more neutrons to try and stabilize it, until eventually we end up starting to cram so much stuff onto it that what happens? It starts to fall apart. Okay? So when we're looking at radioactivity, what we're looking at is the nucleus is literally so massive that it can't actually stay together enough. We've put so much glue in there that now the glue doesn't have anything to hold on to, and it just falls apart. Those pieces that fall off of our nucleus are what we're looking at when we look at radiation. Okay? Okay? So that's what we're evaluating when we're looking at radioactivity. We're trying to see what pieces come off of our nucleus. Okay? Why would they change? Why would those attractive forces between everything change? That's because we've either built up too much of a positive charge, or the neutrons aren't strong enough to be able to hold them together, and we start to break off small pieces. Okay? Why would we break off pieces instead of add more pieces? Okay? If we try and build a cake, we can build it higher and higher and higher until eventually what happens? It starts to fall. Okay? If we continue to build that cake upwards, which part falls? Does it fall and the whole thing completely demolish, or do certain pieces of it stay together? You all have built cakes, right? Really tall cakes? No one? Okay. Typically when things break apart, they break apart in small sections coming off first. Okay? So when we're looking at these forces suddenly changing, it's because those nuclear atoms end up shifting around and moving. Okay? All on their own, just like electrons shift around and move. If for some reason in that random shifting process we get two protons near each other, and we don't have enough neutrons to actually negate that repulsive force, what happens? One of them gets kicked out of the nucleus. Okay? Or other possible combinations of things getting kicked out. Okay? So what we're looking at is that these things are constantly being shifted. As they interact with each other, we constantly potentially see the interaction for something kicking and ejecting out of each of these nuclei. Okay? Yeah, so that's effectively everything that we've just said there. Okay, questions about that? No? Okay, so let's look at the possible ways that we could decay. Okay, so there's a whole bunch of different types of radioactive decay processes. We already talked about the potential for one, two protons getting near each other and ejecting from the nucleus. Okay, that ends up being a fairly rare one. In fact, I don't think that even happens. Okay, so we end up with three possibilities here being our decay processes. So something getting ejected from our nucleus. When we look at alpha radioactivity or alpha emissions, what we're looking at is a full-on nucleus is getting kicked out of our nucleus. We're looking at the loss of a helium nuclei. How would we represent a helium nucleus? If we looked at symbols. Don't all jump in at once. It's helium, so we could go with the easiest place to start. He. The mass of a helium nucleus is 4, and our charge on that nucleus is 2. So if we're going to look at an alpha decay process or an alpha emission, that helium nucleus must be ejected from our starting or our reactant, which means if we were going to write out a balanced equation, where would that particle show up? Left or right-hand side of my equation? On the right-hand side, because it is a product. It has to get emitted from the nucleus. It's breaking off and away from it. Okay? So we could look at an equation. Uranium does have the potential for an alpha emission. What does it become after the alpha emission? So what is X? So we take a look at a uranium nucleus and we say it undergoes alpha emission or alpha radioactivity. What happens? We for sure know that one of the products has to be that helium nucleus. What is atom X? I really talked that long, or are you guys that fast at figuring it out? All right, how do we figure out what it's going to be? All right, how does that work? What are you doing to figure that out? Got the right idea? We started at 238. What happened in the course of the reaction? We lost 4, which means 238 minus 4, which gives us 234. So we know the weight of our species is equal to 234. What's our charge? We started at 92 and we lost 2, which gives us 90. What species is identified by those characteristics? Where did it go? There it is. Some of you already said it. We have thallium. Whoops, gave it to the wrong person. Yeah. Hi. What happens if we do a beta emission? Different isotopes. Okay. So your mass may not come out exactly as the periodic table because the isotope is different. Okay. So don't be concerned about it not matching the periodic table because it probably won't. Okay. At least for the larger ones. The smaller ones, those nuclei are so small that we don't have to worry so much about that proton emission. So typically when we look at radioactivity, it's almost always on the lower end of the periodic table. There are a few exceptions to that, but in most cases that's where we're at. Okay, that's where we see the primary source of radioactivity. Okay. What happens with the loss of an electron? We look at a beta particle. What would our symbol be? We're looking at an electron which has what mass? And its charge? What's the charge on an electron? -1. How is an electron found in the nucleus? That one seems a bit odd. What particles show up in the nucleus? Protons and neutrons. How in the world does an electron come out of the nucleus if the nucleus is only made up of protons and neutrons? So we said protons have a +1 charge and 1 mass. What happens if I take an electron and a proton and I add them to each other? What do I get? The atomic mass would be 1. What's the charge? 0. What atomic particle, or atom for that matter, has a mass number of 1 and no charge? A neutron. Where is an electron coming from? It's the destruction of a neutron. A neutron in the nucleus is now falling apart and becoming a proton and an electron. Do electrons exist in the nucleus? No. So what happens? It must immediately leave the nucleus as a beta particle. Okay? So if we go through and take a look at this reaction, let's say iodine. Okay, if we start with iodine here, and it undergoes beta emission. What's the particle left over? Same thing as we've been doing, add up our atomic weight, or sorry, subtract our atomic weight. So we'd get 131 minus 0. Oh, that jumped too fast. And we go through and look at our atomic number. It's 53 minus, because we're still losing this particle. What is the charge on that particle? -1. If we minus the -1, what happens? We're effectively adding 1, which means our atomic number becomes 54. What particle matches? Hopefully it's up there. We've got xenon. Okay? The beta emissions are going to be a little bit tricky. Why are they trickier than, say, the alpha emission? It's all because of the negative charge. Okay? You have to watch out for your signs and make sure you use those signs appropriately. So when we go through the beta emission, we're losing that electron because it's a loss. We can then subtract across our reaction, and we can generate what our new particle is. Go through it slowly and stepwise, write it out. Hopefully you won't make a mistake. Okay? If you try to skip, the most common one with a beta emission is typically people will tell me it's tellurium, Te. Okay? Why? We go, oh, I lost this particle, so it must have gone down. Not necessarily. Okay? Kind of makes sense? Okay, what happens with a positron emission? This is an interesting one. It's the loss of a positive electron. What kind of symbol should we come up for that? Okay, what letter symbol should we use? E, why E? Because it's an electron. What is the mass of that electron? 0. What is the charge on that electron? +1. Okay? Now that we know what the particle is, if we go through positron emission, we could go through... Yeah, it's all sorts of weird stuff. It comes back to how we end up building nuclei and what different particles come from. So it's how the neutron itself decomposes. Okay? And in the process of that, we can potentially generate a positive electron. Okay? So if we take a look at carbon, so this one happens to be fairly rare. It's fairly low on the periodic table. Carbon-11 does undergo positron emission. What is atom X in this case? Same thing that we've been doing. If we lost the positron, it's going to be our mass number 11 minus the mass number of our positron being 0. 11 minus 0 is still 11. If we take a look at the atomic number, it's going to be 6 minus 1, which gives us 5. And we are now looking at boron. Okay? I'll see what I can't find out about positron existence, where they're exactly coming from, so I can give you a better answer than neutrons just do crazy stuff. But at this point, you just need to be aware that that's what's happening. Okay? So what we're doing when we go through with these transitions is that we're now learning how to balance reactions yet again. Okay? So it's a new type of balancing. Instead of balancing atomic or atoms or even charges, we're now having to balance our nuclear components. Okay? Both our neutrons and our protons in the course of a reaction. Okay? What do you guys think? Straightforward? Okay. Why did I do that? Okay, we can do some other kind of transformations. Gamma radiation. Any idea why I drew it in green? Hulk. How was Hulk created? Created allegedly through gamma radiation. So there we go, green. Okay. Gamma radiation is an energy loss. Okay. Tends to be very, very, very high energy. In fact, I think it's the highest energy you can get. Okay. And what we're looking at is the emission of high energy particles. Those particles have to eventually slow down or be emitted with some form of energy. So typically when we go through and do the alpha, beta, or positron emissions, we would also see some form of energy released at the same time. That energy, because it's effectively an electromagnetic spectrum, has what for a mass? How much does light weigh? Nothing. What is the charge on light? Nothing. So we typically don't show it in our equations, but probably in the case of all of these, we would also see a gamma emission. Should have picked green. Whoa. Should have picked green for that. Oh man, I'm doing it again. Okay. We would also see an emission of energy associated with that. We're going to come up with ways that we can calculate that energy in a little bit, probably a little bit today. But at this point, you just need to be aware that we're just looking at some energy loss in the process of this radioactivity. Okay? This can be one of the reasons why radioactive species are dangerous. Okay? If we take a look at visible light centered somewhere in the middle of that electromagnetic spectrum, okay? If we shift towards the purple color, we eventually become what form of electromagnetic radiation? Ultraviolet light. Are we concerned about ultraviolet light at all? Yeah, leading cause of cancer, I believe even in this state, okay, because of that sun exposure. We get lots of ultraviolet light, okay, and that's because it's higher energy. It can cause different excitations and cause DNA to degrade, and we end up getting mutations that can then propagate and make things worse for ourselves. Okay. Where is gamma radiation as far as visible light goes? Several orders of magnitude higher in energy. Okay. So if we're concerned about a little bit of UV light, guess how much concerned we're going to be about gamma radiation. Okay. There's a massive amount of energy stored in gamma radiation. It's extremely dangerous. We don't want to be exposed to it. Instant death to spite Hulk. Okay. So there isn't really a notation that we would go through for this. Sometimes you'll see it when we lose a particle. Other times it can just be a rearrangement of the nucleus. Remember, the nuclear particles are shifting and moving constantly. Those positive charges and neutrons are shifting around within that space. As they shift around, they might find a lower energy situation. When they hit that lower energy situation, the energy must be released somewhere. That energy will get released as gamma radiation. Okay? Sometimes we'll also see this if we collide positrons and electrons. So if you go into any of the hadron colliders or anything like that where they collide these particles, you'll sometimes see gamma radiation in those cases as well. Okay? One of the last transformations that we'll look at will be electron capture. Slightly different than the other ones. The other ones we looked at in emission. Something was leaving the nucleus. What do you think is happening in electron capture? It's coming into the nucleus. Okay? So what happened is our nucleus got so large that that first shell of electrons is now so close to that positive charge that what happens to it? It gets pulled into the nucleus and we end up adding an electron as a reactant. Okay? So our symbol for electrons would be E. What's the charge on an electron? And our mass? 0. So we're now adding this electron as a reactant in the course of a reaction. Whoops, there's our gamma radiation. What would atom X be in this case? We go through and do the math. Let's see if I did the math. Okay. Our atomic numbers, whoops, that should have been a plus. The sign in between will now be a plus. Why would we use a plus in between as opposed to the minus that we had before? Where is the electron? Is it a product or a reactant? Where's the electron? It's a reactant, which means we are adding it to our nucleus. If we're going to add it, we should use the positive sign, not the negative sign. So we take 127 plus our 0 charge or our 0 mass for our electron, and we get 127. When we go through to look at the atomic number, 53 was our iodine. We will now add our electron. Our electron has what charge? -1. When we add a -1 to our number, our atomic number drops and we get to 52. We end up with tellurium. Okay? Questions about any of those transitions? Okay. As far as these problems go, what you will see on the exam is very similar types of questions. Predict what X is. X can be a product. It could also be a reactant, depending on what I feel like asking. Okay? It could very well be that I give you, in this case, iodine and tellurium, and ask what process occurred. Okay? You would then go through and figure out the difference between those two and say what that particle had to be. Okay? Make sense? Okay. Other questions that can get kind of obnoxious with radioactivity. You are responsible for knowing what electron capture is. You are responsible for knowing, I have to go back quite a ways, that an alpha particle is the loss of a helium nuclei. You are responsible for knowing that a beta particle is the loss of an electron. Okay? So you do need to have that memorized, what each of those individual names mean, what they apply to as far as your reactions go. Okay? Yes?
Is the alpha just like the loss of the helium?
Just the loss of a helium nucleus, yeah. Okay? Questions about that? As far as your homework goes, I'm pretty sure both Sapling and Connect have a couple problems, or maybe one problem, where you're going to do multiple transitions. Okay? So we say we start with, say, uranium. It undergoes alpha emission, followed by beta, followed by a second alpha, followed by another beta, followed by two more alphas. What's the product? Okay? To go through and do that, stepwise through. Okay? Add, subtract, do whatever you need to for each of those possible transitions to end with your final result. Okay? It may take a little bit more time, but you are responsible for that. At most, I'd probably throw one question like that on the exam. For the most part, I just want to see that you understand what these individual pieces are. Okay? Any questions about these? Okay. Yes. Yeah. That 2 in front, typically what do we do with a 2, with any number when we put it in front of something? What's it mean? It's the number of them, right? So the 2 in front in this case represents 2 gamma particles. Okay. Oh, there's another problem here. So yet another way that we could look at this, I could ask, give you this problem, what is atom X in this case? So we're looking at the reverse thought process. Okay, should we go through and do that one? Yes, no. No. Moving on. I definitely did not include a slide on this, so before we get into the manipulations, back when we look at possible radiations, how can we predict whether an atom, or a nucleus, is going to go through radioactivity? Okay, we talked about one possibility. What's the likelihood of being radioactive up in the higher numbers, say 1 through 18, versus being radioactive between 90 and 103? Which one's more likely to be radioactive? Numbers, elements 1 through 18 or 90 through 103? Probably 90 through 103 because the nuclei are much larger, which means we have to have more protons and neutrons in there. Eventually we get so large that it just starts to fall apart. Okay? So we would expect higher numbers to be more likely to be radioactive. That's a very hand-wavy argument because we're just kind of guessing at it. Someone has gone through, or several people have gone through and have studied radioactivity across the periodic table, and they've ended up discovering something known as the belt of stability, I believe. And that's not a +3 belt. That just means that those atoms or those nuclei are particularly more stable than anything else. Okay? So they would not be expected to go through radioactivity. Okay? What we're looking at least in the lower levels, is we're approximating for every positive charge, we would expect 1 neutral charge or 1 neutron. So if we plot that out, we'd get a nice straight line. At the lower ends of our periodic table, those elements happen to track very nicely along that. For every neutron, there's a positive, or sorry, every neutron there's a, what's the positive one? Proton. Okay? As we get further up through the periodic table, we end up putting so many positive charges in there that we need more neutrons. So the belt of stability, actually I think I can draw this. And I'm undoubtedly going to plot this wrong, but if we look at our neutrons versus our protons, it's pretty much a one-for-one track. So we get a line with a slope of, what is that, 1? 1 over 1? Yeah. Okay. And if we were going to plot the different elements with their reactivity, we could go through and say, in most cases, our non-radioactive species happen to balance pretty much along that line until we get up into higher weights, and eventually we start to skip off of that line. That's not very easy to see. Let's do some bigger marks. Okay? And we see a little bit of a bend on it. Okay? And that's because as we get so much larger, we need more neutrons to stabilize it. So I definitely plotted it backwards. Okay? Since I plotted it backwards, I know that, and I can fix it. So what we can go through and do is, I just wrote the same thing. What we can go through and do is look at an individual atomic structure or a nuclear structure and decide where it falls with respect to this line. Is it something that falls up here, or is it something that falls down here or somewhere on the line? If it's on the line, would we expect it to be radioactive? No. If it's above the line, that means we have too many protons. So what should we do? Some form of radioactive decay that gets rid of protons. Okay? If we're below the line, that means we have, neutrons. I keep plotting it backwards. If we're below the line, that means we don't have enough protons. So what we're going to have to do is do something that can increase the number of protons. Okay? How can we increase protons? Electron capture, right? Does that increase your number of protons? One of them increases the number of protons. I don't have them memorized. I'd have to draw them all out. Okay? Your textbook goes through and does a much better job of discussing this. The only reason I'm addressing this is that I know there are questions in the homework. So you are responsible for reading up on it in the textbook. It's not a question I would ask on the exam because it requires strict memorization. Okay? So what I expect you to be able to do is to do the nuclear transformations. I don't expect you to answer any questions on that belt of stability as far as the exam goes. To do your homework, you will undoubtedly have to open up the textbook and take a look at what it describes. Because if you end up being above the line, there's a particular type of radiation that allows you to drop back down to the line. Okay? If you're below the line of stability or the belt of stability, there's a particular type of radiation that allows you to get back up towards that line. Okay? Does that make sense? Okay? So read the section in the textbook that explains that. I think there's 2 questions in both homework assignments, both in Sapling and Connect, that are going to require that you read that material to be able to answer those questions. Because I certainly did not do it justice here. Okay? So individual manipulations. Okay? Once we get kind of a ground rule set up on what's going on, the rest we just kind of add and subtract. So we've looked at our transmutations, or we haven't looked at transmutations. Transmutations are taking multiple different atoms and now smashing them towards each other. Transmutations was ultimately where chemistry started, back with the Philosopher's Stone, trying to turn anything cheap into gold. We were trying to transmute lead and make it gold, so we could be tons of, or super wealthy. Okay? So when we're looking at transmutations, what we're doing is now adding and subtracting different nuclei in different fashions to try and generate new nuclei. Okay? So a transmutation might involve smashing lead atoms against something else. Say, smashing it against an electron, what happens? It could be as complex as taking a lead atom and smashing it against an oxygen atom. Okay? What's the end result out of that? Okay? So it's just a question of adding and subtracting your different species to end up with new atoms. Yes?
Was this the same thing that they used in 45 or whatever when they changed the irradiance to U235 or whatever that number is to make it more, I mean, is it?
I don't know that, but quite possibly. Typically, I would say no. With the transmutations, you aren't doing it on a very large scale. To get two nuclei to interact, you have to be able to get their nuclei to literally touch each other. But what's around each nuclei? Electrons. What happens when those electrons get near each other? They repel. As we get closer and closer, we get the electrons even closer to each other, which then causes them to repel even more. But then not only do we have that, but we also have the two nuclei now getting really close to each other, and they also want to repel. So to be able to do transmutations, we need an incredible amount of force to jam those two nuclei and get away from that repulsive force. Okay? To do that, that's where we have the large atom colliders, okay, where we smash atoms together. So yes, it works to generate a new atom, but at what scale? You just smash two atoms together to make one. Woohoo, I have one atom. Okay? When the scale that you would need, particularly for radioactivity or energy, you're looking at mole amounts, if not more than that. So the transmutations are typically not something done on a large scale for that reason. Okay? Other applications that I think I want to look at tomorrow, so we'll probably end this early. We're going to start looking at radiometric dating, which brings in time. What chapter do you think is going to involve time? The very first one we started with, our kinetics chapter. Okay? I know we took a nice long break from kinetics, but we're going to come back to that when we look at dating individual species. We'll also look at half-lives. So it comes down to kind of a safety system. If we know there's a particular radioactive source, say, geez, where did they just have that plant blow up? Don't tell me Japan. Where in Japan? Here, that's the bombs. Yeah, last year. Where was that?
Japan?
Yeah, where in Japan? They had that plant during the tsunami that got destroyed and ended up leaking out radiation. Okay, that's where we destroyed a bomb. Different thing.
No, that's Hiroshima.
Oh, what did you say the other one?
Fukushima.
Oh, Fukushima. Yeah, Fukushima was the name of the plant. I do remember that now. Okay, we now know there's lots of radiation there. When is it now safe to allow people back to that plant? That radiation is dangerous. Okay? So it might be a good idea to have some idea of how long it's going to take for that radiation to be minimized. How do we figure that out? We have to go back to kinetics and look at how long it takes for each of those nuclear transformations. Okay? So that takes time in kinetics, so we'll have to go back to that material. Thankfully, when we go back and look at kinetics, we are going to make some simplifications. When we looked at kinetics, we had zero order, first order, and second order. Of those three, the only one we're going to be concerned about is first order. Any ideas why only first order? Zero order meant nothing happened, right? So that's probably out. Second order means what? Two things had to come together to do the reaction. When we look at these transformations, how many things do we have? We have one nucleus. All of these transformations are first-order decay processes. So when we go through and look at the radioactivity and kinetics, or the kinetics of radioactivity, we're only concerned about those first-order transitions, which will make life a little bit easier as far as calculations. We'll talk again briefly about detecting individual forms of radiation. That's going back to the Geiger meter. And then we'll also address how it is a useful source of energy, which brings us back to Einstein's famous E equals mc squared process. So we'll go through and solve some of those problems, and we'll do that, what is it, Thursday, tomorrow, right? Okay. I would guess we're going to be darn close to done with the material on Thursday, which means I will try and set up Monday being kind of a review, more based on the radioactive portions of it, probably going through some homework problems to make sure that you guys get those figured out and squared away. Tuesday will be a straight review of, or not a review, Tuesday will be a discussion of applying future courses of chemistry. So we'll look briefly at inorganic chemistry and color, and then we'll look at some organic chemistry type thoughts and what you can expect to see in that class if you have to take that. Okay? Wednesday will be a strict review. Come in with questions. Otherwise, all you'll see is me rehashing old slides and probably pointing out where I think there were weaknesses. Okay? Biggest weakness? Come on, you all have taken all the tests. You should know where your biggest weakness is. Where's your biggest weakness? Acids and bases. Okay? So because of that, you can almost guarantee the acid-base chapter, as far as questions, will not be repeats. Okay, on your final. I want to see that you can actually solve those. So the questions that you will get as far as show your work from the acid-base material will be actual new problems. Okay? You need to show and prove that you can do those without just memorization of old stuff. Okay? So, if you got any questions, come up and ask. At that point, we're done. Stop.